Hello and welcome to our lesson on polynomial functions. In this chapter, our objectives are to find factors or zeros, or sometimes solutions are called, by factoring and by division, and also to describe key features of higher degree polynomials, and we're getting into that in this lesson. By the end of this lesson, you should be able to say that you can identify the degree, leading coefficient or LC, and zeros of a polynomial, as well as describe some key features of a polynomial from graphs as well as equations. The degree of a polynomial is the same as the greatest exponent of the variable, and we're going to be using x. The leading coefficient is the coefficient of the highest degree in the polynomial, and that's a term in the polynomial. A zero of a function, f, is an x value, and we'll usually call it c, for which f of c makes the function equal 0. So we're not inputting a 0, we're getting out a 0, or an x-intercept. A turning point occurs at the bottom or top of a curve, and also known as a max or min, and a local max or min. Finally, an inflection point is a place on a graph where the concavity changes, and we're going to get into some of that stuff. Polynomial functions, just in general, something to look at here. We'll see that the degree, the highest degree, has names. In this case, a quadratic is a degree 2. The highest exponent here is a 2. I could have listed linear, that's a degree 1. Cubic, degree 3. Quartic, degree 4. Quintic, degree 5. We want to find the following for the functions below. We want to be able to find the degree and the leading coefficient. So if we look at this function here, it's got a 3x to the 6 minus 7x to the 5, and it keeps descending, you can see, and the highest exponent is 6. That makes it a degree 6. The leading coefficient is the number in front of that term, and that's a positive 3. For the g of x function, we can look at, it's a little bit tricky, we can see that the 7 is an exponent for x squared, but it's not in the front. We would say this isn't in standard form. So the degree is 7, its leading coefficient then, if it was in standard form, negative 4 would be in the lead, so to speak, in the front. And then finally, here's a quadratic. H of x equals x squared plus 16. And we'd see that the highest degree is 2, it's a quadratic, as well as the leading coefficient. You can't see it, it's a 1. The fundamental theorem of algebra states an nth degree polynomial function has exactly n zeros. And we're used to the real zeros, it's where it crosses the x-axis. Also the complex ones, if you remember the quadratic formula, whenever the radical, it's called the discriminant, is negative, you get the square root of a negative number. That has an I in the answer, and those are going to be complex or imaginaries. So the number of zeros, like for instance in this h of x equals x squared plus 16, it's got 2 zeros because the highest degree is 2. And if you think about it, you can't square a real value and get a negative 16. We need h of x to equal 0. So this would have a value like 4i, or negative 4i. Because when you square the I, you get I squared. That's a negative 1. Anyway, so that's a complex 0. But more commonly, if we look at this f of x, we see there are 6 zeros, because the highest degree is 6. And then likewise on this last one, the highest degree was 7. We'd expect 7 zeros. Some might be real, some might be complex or imaginary. And now we'll take a quick look at some terms that we use. Turning point. Turning point is kind of self-explanatory. It's where the graph turns and changes direction. So on the left side of a turning point, in this case, it's increasing on the left, decreasing on the right. If we go down to this middle one here, the graph is decreasing on the left and then increasing on the right. The turning point is that place where it changes that direction or concavity. Zeros, we pretty much know it's the value of x that makes the function equal 0. And then the inflection point, that's the subtle place where how much things are changing changes. So for instance, the inflection point that we'd see on the left here, this is where the graph is decreasing faster and faster, and after the inflection point it decreases still, but at a slower rate. Likewise on the right, we see a increasing graph at a faster and faster rate, kind of like an exponential you could think of, but then past the inflection point it's still increasing, but now at a different rate, at a slower rate. Consider the zeros for the following quadratics, and these are going to be parabolas, their graph. How many zeros, how many real zeros would we see here? For this first graph, we'd see 2 real zeros. They're always going to have 2 zeros. This has 2 zeros, but it looks like it's just 1. What's unique about these zeros is we call them a double zero or a zero of multiplicity 2. The value, in this case, it looks like 1, 2, 3, 4. The value x equals 4 makes the function equal 0. We would say it does it twice. That's a double zero. What's unique about these zeros here? Well, these zeros don't cross the x-axis, the real axis, so we're going to say that these are imaginary or complex. So if we were to look at what we've just seen here in a table form, a polynomial of degree 2, and we're going to be building this as we go through the lecture, called a quadratic, is going to have 2 zeros exactly, and if we remember, that's from the fundamental theorem of algebra, that the number of zeros equals the degree, the highest degree, highest exponent of the polynomial. The number of possible real zeros, you could have none, as we saw in the last example where it doesn't cross the x-axis. They'd be imaginary or complex. Could have 1 if it bounces off the x-axis. That's a double zero or zero of multiplicity 2. And finally, if it crosses the x-axis twice, like we saw in the first example, the vertex is below the x-axis and it opens up. Or you could have a vertex above the x-axis where the parabola opens down. And the max number of turning points going from increasing to decreasing is exactly 1 for those. And now let's take a look at some graphs of cubic functions. We have a y equals x cubed. It looks like a direct variation there. It goes through the origin. It has a single zero, you could say, in terms of real values, but it has multiplicity 3. So we would say it is a triple zero. It has 3 real zeros. They're just all the same value. In this case, we cross the x-axis in 3 different places, so each of those zeros has a multiplicity of 1. No multiplicity, you could say. I've shifted this graph over a little bit. You see that it has the 1 value of x that makes it equal 0, 1 value that's real, but it's a multiplicity 3. And then over here we have a graph that bounces off the x-axis. That creates a double zero at x equals 2. This one could have been shifted up a bit, and then we just would add 1 0. So it's possible to have 1 0, but not no zeros. And if we take a look at the information in table form, cubic functions, degree 3, have exactly 3 still by the fundamental theorem of algebra. You must have at least 1, though, 1 real zero. And that's if it curves and doesn't get back down to the x-axis before it curves back up. 2 if it crosses the x-axis twice. And then 3 if it crosses the x-axis straight through in all 3 places. We had that double zero that caused for 2 zeros in the example. So we're going to have at most 2 turning points. There are some inflection points that could be a little bit confusing, like in that y equals x cubed. Didn't look like it had any turning points, and it didn't, but it did have an inflection point. So if we keep going here, graphs of quartics, degree 4s. We see the changes here. You can see where there's real zeros, some are double. In this case, we have 4 unique real zeros. In this case, there are 2 real, and since it's a degree 4, there must be 2 complex or imaginary ones. And now to look at a table for our quartic, degree 4, exactly 4 zeros. You could have no real zeros out of those if the squiggles, if the graph came up to but never crossed the x-axis and stayed below or above. We could also have 2 if both bounce off as double zeros or if it goes straight through. We saw examples of that. And then also you could have 4 if it goes straight through every time. We can generalize here. For the max number of turning points for a degree 4, at most you can have is 3. Generally there are a maximum of n minus 1 turning points for a polynomial of degree n. So for a cubic, that would be 2, so 3 minus 1 is 2, and that's the maximum number. Continue and look at now just a graph and try to classify it. What's the lowest possible degree of the following function? Well, you can have n minus 1 turning points, and I see 1, 2, 3, 4 turning points. So since there are 4 turning points, 4 plus 1 or 5, degree 5 polynomial is the lowest degree. Could have more if there's some subtle inflection points. But let's just work with a degree 5 that has the 4 turning points. Based on the answer above, how many zeros? Well, if it's a degree 5, by the fundamental theorem of algebra, we would have 5 zeros. Maybe not all real. How many real zeros does it have, actually? In this case, if you look, It has 1, and then that's a double zero, so 2, 3 we would say, even though 1 has multiplicity 2. And is the degree odd or even? Is the leading coefficient positive or negative? If you looked at some of those graphs, odd are going to end in opposite directions, so this is going to have an odd. Even are going to look like a parabola to some degree. And then it goes like a slope, so if it starts down and increases generally from left to right, even though there's some squiggles in the middle, it's a positive slope. If it starts up at positive infinity and ends down, that would be a negative slope. Or we would think of it as a negative slope and would have a negative. So in this case, it's odd degree. It ends in the opposite directions. Leading coefficient must be positive because it generally increases from left to right, even though there's squiggles in the middle. Now if we want to generalize a bit more, since the curve has end behavior such that on the far left, x approaching negative infinity, that's this notation, the function itself approaches negative infinity, it goes down. As x approaches positive infinity over there on the right, it increases. So we would say we can think of this similar to a line with positive slope. Therefore, the leading coefficient must be positive. We talked about that. If a curve has end behavior such that on the left, as x approaches negative infinity, it approaches, the graph itself goes positive, and if on the right it approaches positive. If you look at this, this is similar to a parabola. It's not a parabola. But we would say for a curve with an even degree, we can think of it as a parabola with squiggles in the middle, and the number of squiggles will help us determine a degree or a possible degree. So let's draw a cubic function with a positive leading coefficient that has zeros at 1, 2, and 3. We're going to want to plot the points 1, 2, and 3 on the x-axis and then do some squiggles. So in this case, cubic function, positive leading coefficient looks like it increases from left to right in general, and it crosses at, I'm going to call these points 1, 2, and 3 for x. Why don't you give this one a try on your own and then hit play. Okay, when you did this problem, you put dots at -3, -1, and 4. The leading coefficient being negative makes it look like it decreases from left to right. A graph like this would work. Okay, go ahead and read this one and try it on your own and then hit play. Quintic functions are degree 5. All right, well here's two different, they're unique in that there's a double zero on the left here, single zero on the right, single zero on the left, double zero on the right, still decreasing generally from left to right with some squiggles. All right, this last example says to draw two unique quartic functions that have a double zero at 3 and zeros at 1 and 5, and also a y-intercept of 6. And so what you're going to want to do is put dots at 1, 3, and 5 along the x-axis, put a dot at 6. And I'll just tell you it's very, very challenging to do this. So go ahead and pause and give it a try. Okay, well if we put all our dots where they need to be, we see that to get a double zero at 3, the curve would come down, open, it has to open up here, and then go through 1, bounce off, turn around, go back up, and go through 5. So we'd still have 1, 2, 3 turning points. It works. Now, you can't do it any other way. You can't have this open down. So I went ahead and tried to draw it, and it didn't work. If you go ahead and try this, I can make it work, but I have a problem making it an even so it opens down and having only 3 turning points. In this case, I have 1, 2, 3, 4, 5 turning points. So this is actually a degree 6. This one does not work. We can only do 1. When we start to specify this information, it gets more and more challenging. So with that, give a try for the on your own, and we'll see you in class.